So once we talk about, I want you to have this in the back of your mind, that this relates to some of the questions for Lab B6. So ionic compounds, and this is still 12, 16, 14. You know that it's a bunch of positive and negative ions that are standing shoulder to shoulder because they're so darn attracted to one another. So they're not intermingling their orbitals. There is no intermingling of orbitals. They are just standing shoulder to shoulder. They're touching. But how hard is it to pull apart cotton candy? Yeah, you can pull apart cotton candy pretty easily. These things are like two, oh, I should have bought my rare earth magnets. Dag nabbit. These things are held together really powerfully. These are like two very strong magnets with opposite poles being held together. For the most part, ionic compounds tend to be solid at room temperature, and they tend to be what we call crystalline. Now, when I say crystalline, what do you think that means? When I say crystal, what comes to your mind? Stalactites, okay? That. What else? Rock candy. What else? Salt. What else? Pretty little crystal pendants that people wear, stones. Okay. Those things are all crystalline solids also. All crystalline means, I mean, ice is a crystalline solid. Seriously. All a crystalline solid means is that it's got a regular, repeating geometric structure. It's not randomly tossed together. There's a very regular structure and shape to the way that the atoms, or ions in this case, are arranged. And most ionic compounds are these crystalline solids. Well, what do we know about these crystalline solids? Oops, let me move that down a little bit. So we'll talk more about their properties, but ionic formulas, which we will do extensively in the next chapter, remember that when we had a molecular compound like C6H12O6, that represents one molecule of this stuff, and there are literally 6 carbon, 12 hydrogen, and 6 oxygen. It is a literal interpretation. There is like a shoebox someplace with 6 carbon, 12 hydrogen, 6 oxygen. That many, no more, no less. Not 5, not 4, 8 is right out. I mean, this is it. Well, with ions, it's not like that. With ionic compounds, it's just a ratio. Okay? We said things that are covalently bound you have molecules of. There are no molecules of ionic compounds. No one has ever seen a molecule of salt, table salt. They don't exist. They don't exist. What we have in ionic compounds, instead of a molecular formula that shows the actual number of things in a molecule, is we have these ionic formulas. We show them in formula units. All it is it's a ratio. It's the simplest ratio of things that balance out the charges. So for sodium, what kind of ion does sodium form? 1 plus. What does chloride form? 1 minus. It's 1 to 1. For every 1 chlorine, you'll have 1 sodium. For every 1 sodium, we'll have 1 chlorine. And they're balanced. So the formula unit is NaCl. And you did some formula writing in physical science, no matter who you had. Who you had will dictate how much of it you did. Like I know Mr. Stubbe does a ton of formula writing. Mr. Voorhees does a lot too, I guess. I mean, we all do it. We all cover it. And Mr. Stubbe does extensive work with formula writing. Okay, what if we had magnesium chloride? What kind of ion does magnesium form? Look at your periodic table. Then hold up fingers. Did you actually put your periodic tables away? You're actually attempting to do chemistry without a periodic table? That is a flogging offense. Okay? I see fingers up. It forms a 2 plus. Okay. How many valence electrons does magnesium have? 2. Will it give them up or gain them? It will give them up, which means it's got a 2 plus. So group 1 always forms 1 plus, group 2 always forms 2 plus. That's how we're doing that. Okay, so if we've got magnesium 2 plus and it's bonded to chloride 1 minus, in order for these things to form a little formula unit that's neutral overall, is it 1 to 1? No. We'll have 2 chlorides for every 1 magnesium. And in physical science, you probably learned the crisscross. We'll do that a lot in the next chapter. You take just the absolute value from the charge, and you write it down here as a subscript, and 1s go away. Do you remember that? Sound familiar? Crisscross. You all did it. I can guarantee you all did it. I can 100%. Oh, go talk to your physical science teacher. I'm quite sure that they will say, yes, you did. So, anyway, that gets you your ratio. And we'll do a lot more with getting these ratios in the next chapter when we do chemical formulas. So, all that an ionic formula is a ratio. Nowhere out on the planet is there some little molecule of magnesium chloride, which is 2 chlorines and 1 magnesium. No, we've got a big giant chunk of magnesium chloride that might have 500 magnesiums, and if there are 500 magnesiums, there are 1,000 chlorides. Okay? It's just a matter of ratios. So that's an important distinction. Now, okay, if we have a sodium, can we draw an electron dot diagram for it? Yes, pretty handily. If we have a chlorine, can we draw an electron dot diagram for it? You betcha. Now, if we want to draw the ion, remember ions are always in brackets. What does that represent? Yeah, sodium that's lost its 1 valence electron, it's now got a 1 plus charge. If we want to draw chlorine, having done this, it's got a 1 minus charge. It's picked up an extra electron. So we can represent this, because they're ions, they have to be in brackets, and we have to show the charge. Those are non-optional components. If we wanted to show, in essence, a Lewis diagram for an ionic compound, we could, well, actually, let me make this simpler. We could show these two things sitting side by side. That's it. So that's fairly simple. It's certainly dramatically simpler than doing molecular compounds with Lewis structures. Okay. So we said that ionic compounds tend to be these crystalline solids. They have regular repeating structures. So we'll go back to Cutie Pie and Best Friend, where you'd really like to be as close as possible to Cutie Pie, and you'd really like to be as far as you can from Best Friend. That analogy applies to ionic compounds as well. Except now we're talking about ions rather than just protons and electrons. So if we have, and I will shrink this. Whoops, not that. Just want to shrink. Nope, that didn't work. Select. There we go. Okay. Let's work with our old friend sodium chloride. So, every sodium we're just going to represent with that. And every chloride we're just going to represent with that. Okay, great. So we know that they're going to line up so that all the sodiums are near all the chlorides and all the chlorides are near all the sodiums, right? Fantastic. Well, what about the next row? Well, they're going to be offset, Moser. Come on, that's ridiculous. That's easy. I get it. I get it. I understand. Sure. Yeah, I got it. I got this. I get it. It's not that hard. And it's not, in point of fact. So you see how we're building this regular repeating pattern. And we could go on all day long. But we're not, because that would just be ridiculous. Cut. Cut. Okay, so you get the picture. We get this nice repeating pattern. If we were to look at this on a molecular level, we would find that we would have basically even distances we would have distances in all the directions that are the same throughout the entire structure, through the entire crystal lattice. Everything would line up at the same distance. What was the thing that controlled how far apart two atoms were in a molecular compound?
Bond length.
Well, bond length is the description of that distance. What controlled it? Yeah, attraction and repulsion. Cutie pie! Best friend, you know. Wanting to be at a point where the attraction balances the repulsion. And so they lock into place in this lattice. And if you've ever seen latticing on a house, you may have flowers growing up a lattice someplace. They sell it at Home Depot. They sell it at, 84 Lumber and Beaver, whatever. And it's just repeating strips of wood. That's lattice. Now imagine at every intersection is parked either a chlorine or a sodium. That's what we're looking at. Now when we get into ratios that are not one-to-one, obviously some things change. But what remains the same is that this is a repeating geometric structure and it's locked in place. And you have got so much attraction going on here. So much attraction. Every positive in there wants to be next to every negative in there. Every cation pulling towards every anion and vice versa. There's a lot of contained energy there. There's a lot of contained energy. We talk about lattice energy briefly. It's because we don't have bond energy in these things, because we don't have the same kind of bonds. Lattice energy is basically the energy contained in that force of attraction. We won't get into a whole lot more detail. It's actually technically the energy released when 1 mole of ionic compound is formed from a gas, but we don't worry about it a whole lot. That's some powerful attraction, though. This is like a 8th grade dance. It's disgusting. It's like, yeah, it's just a lot of overwhelming, like, oh my gosh, I don't want to see that kind of attraction. Maybe it's more like Sadie's. I don't know what happens. I hear things. It's a lot of too much. This is like avert your eyes. Could you two please take it someplace else? Except it's all of them, all at once. It's repulsive to a non-ion such as myself. But it's a lot of attraction. There's a powerful force in there. Okay, so let's go back and borrow our little chunk of ionic compound here. So here's our ionic compound. We'll say that this is salt. If we have a molecular compound, well, let's take methane. Methane's a nice, simple molecular compound. Cow farts. And this will stand in for sugar or anything else. Inside an ionic compound, there is so much attraction there. There is such a powerful force of attraction. These things tend to be really hard to basically separate those ions. So when we take, well, let's make this sugar. When we take sugar, I'm going to do a terrible, terrible job of drawing somewhere my organic chemistry prof is getting a pain in his neck. Anyway, I'm just putting a bunch of hydrogen and carbon in there. It's ugly. Let's say this is sugar. This is in no way representative of the structure of sugar. I just want to tell you that. These things are sharing electrons. The individual atoms are held pretty tightly together. But what's holding this sugar to the next sugar over? Yeah, there are some intermolecular forces. It's not that big a deal. Nah, we could go someplace else. You can melt sugar pretty easily. You can turn it from a solid. What happens when something goes from a solid to a liquid? The individual units, whatever they are, have to separate so that they have more space between them and they can flow past one another. Well, with molecular compounds, it takes a chemical reaction to break apart that molecule. But some simple heat will melt that. Molecular compounds tend to have low melting points. They tend to be capable of being melted at very low temperatures that you can achieve with something like, say, a candle. Ionic compounds, not so much. So because you've got all these forces of attraction running in all these different directions, you've got, attraction here, attraction here, attraction here. This is a tight network of forces of attraction. These things tend to not melt real easily. Like 3,000 degrees Fahrenheit will melt you some salt. That's hot. You're not going to do that with a candle in a chem lab. I think whatever was going on is being resolved. You can't melt ionic compounds at low temperature. They tend to have very high melting points and boiling points. So it's hard to get them to go from a solid to a liquid. It's hard to get them to go from a liquid to a gas. They tend to be hard, but they're brittle. This is one of my favorite days. I have, and I'm getting low now. You know what this is? Salt. Have I told you guys about the salt mines under Lake Erie? Okay. I got to go to the salt mine, blah, 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 blah. They give you samples. You can take a bag and gather up as many samples as you want. Let me take a picture of my little salt crystal here. And I suppose I should actually take a picture of what I'm going to do to my little salt crystal. There's my salt crystal. So if I drop it, there's my salt crystal. If I drop it, let's see. So when I smash my poor salt right there with a hammer or a chunk of granite, whichever I have handy, it tends to shatter. It's really hard. It's hard to melt. This stuff, get it to 3,000 degrees to melt. Why can I defeat it so easily with a chunk of granite? Well, the answer lies in this bond structure. As long as everything is lined up perfectly, these are very, very strong bonds. What happens when I hit this with a hammer, a stick, a chunk of whatever? What happens is I shift everything. Sorry. I shift these guys down. And when you shift those guys down, suddenly are the forces of attraction the way they used to be? Heck no, this stuff will fly apart when you shift it off. So ionic solids tend to be very brittle because once you shift those ions, the forces of attraction, that network of attraction, is no longer active. It disappears. So they tend to have incredibly high melting and boiling points, but they also tend to be really easy to smash with a hammer, and they will shatter into a bazillion pieces. Now, There's one last thing about ionic compounds that you might find interesting. If you take an ionic compound and you put it into water, it tends to conduct electricity. Huh, that's weird. So what happens, and this is actually pretty neat, we do a lot with this in chapter, man, that's a mess. We do a lot with this in chapter 15. We talk about solubility. Whoopsie. So if you take an ionic compound and you put it into water, and I'm just going to go with what I've got here. Remember we said water has got some areas of charge? Water has got some areas of charge. So that water manages to snake its way in between all these ions, and it separates them like a border collie with a bunch of geese. Just splits them all up, moves them all around. Well, now you've got a bunch of water with a bunch of ions in them, which have got electrons that they can give up, trade, share, not share, but they can flow. And so those aqueous solutions, aqueous just means water, tend to be really good conductors of electricity. Huh. Thinking about your lab B6, do you suddenly have any suspicions about the identity of the compounds in your two groups? What are your suspicions? You had 3 substances that you couldn't get to melt at lab temps with a candle. And then if you look at their other characteristics, sure looks like they might be ionic substances versus moleculars. Okay. So we'll stop right there. You'll need to make sure that lab B6 is turned in by tomorrow, so by 12/17. And tomorrow we will grade this chunk of homework. We will do a Lewis Structures FIP quiz. And you know what? I may do this. I'll tell you how I'll do this. I will do this as a take-home FIP quiz. So how is a take-home FIP quiz different than homework? It's not necessarily, but remember that FIP quizzes are what? Not for me. They're a pain in my tuchus. They're for you. They're to see, okay, when I am faced with nothing but 4 Lewis structure problems and a blank sheet of paper, and I don't have my notes, and I don't have my book, can I do this? So I'll give you a Lewis Structures FIP quiz for take-home tomorrow. Thursday when you come in, I will also give you your holiday ornament lab. Thursday when you come in, the answer key for the Lewis Structures quiz will be in the hall. It will be up on PB Works. You're responsible for checking it yourself. It's on you. You're responsible then for reporting your grade on it to me. So you'll email me your grade on that quiz. Thursday we will be doing the holiday ornament lab. My lovely lab assistant is currently taking care of your acetone wash ornaments, which saves you a bunch of time and enables us to get this lab done in one lab period. We do some structural things to accommodate getting this all done. If you are not going to be here on Thursday, you can make time to come down on Friday and you can make an ornament. If not, you'll just be responsible for some of the math. It's more fun to get to make an ornament if you're going to have to do the math anyway. But Thursday we will be making ornaments, and it is a blast, and a ball, and some shattered glass often. So we'll see how far we get without breaking glass. We'll see if you guys can set a new record of being a class who doesn't break any ornaments. That would be awesome. The dustpan and the broken glass box get a workout during ornament day. Okay, questions, comments, concerns? That's it.